Check this out. I'm going to show you how. Okay, you ready? All right, $118 for car insurance. That's how much I was paying, okay? I picked up the car.
But when you look at it, there's a lot of really uncommon things like ahead or ollie and arg, the kind of words that bring about family arguments in a game of Scrabble. But the vibe of the game is that the answer is always going to be a decently common word. And in fact, there's another list of around 2,300 words that are the possible answers. And this is a human curated list. I think specifically by the game creator's girlfriend, which is kind of fun. But what I would like to do, our challenge for this project, is to see if we can write a program solving Wordle that doesn't incorporate previous knowledge about this list. For one thing, there's plenty of pretty common 5-letter words that you won't find in that list. So it would be better to write a program that's a little more resilient and would play Wordle against anyone, not just what happens to be the official website. And also, the reason that we know what this list of possible answers is because it's visible in the source code. But the way that it's visible in the source code is in the specific order in which answers come up from day to day. So you could always just look up what tomorrow's answer will be. So clearly there's some sense in which using the list is cheating. And what makes for a more interesting puzzle and a richer information theory lesson is to instead use some more universal data, like relative word frequencies in general, to capture this intuition of having a preference for more common words. So, of these 13,000 possibilities, how should we choose the opening guess? For example, if my friend proposes weary, how should we analyze its quality? Well, the reason he said he likes that unlikely W is that he likes the long shot nature of just how good it feels if you do hit that W. For example, if the first pattern revealed was something like this, then it turns out there are only 58 words in this giant lexicon that pattern.
Now it's like probability of word given basically like W, and there's an A in here somewhere. It's like W, 1, 2, 3, 4. There's an A in here somewhere. And I guess this one is like anything but A. Probability of some event. If it's the probability of this event, then that's a probability of 1. But yeah, what you're really doing is starting off with the sample space, which is just equal to the vocabulary size. And then when we hit weary like this, we've got all the words that start with W over here, and these get crossed off. And now we're just remaining in this universe of words that start with W, narrowing down the sample space significantly. So the sample space is, the possible outcomes. So the experiment is like it's today, and there's a random word, and yeah, our probabilistic experiment is we like draw a word, and yeah, so the sample space is the vocabulary, and yeah, when we get information, so we kind of start off with our sample space here, we get information, and then we're like, some event happened. The event W star is this event. So all this kind of like goes away. And like this is the only thing that's remaining. So we're now like in this conditional universe, crunching down the sample space. So that's what we're doing. We're successively like crunching down the sample space.
That's a huge reduction from 13,000. But the flip side of that, of course, is that it's very uncommon to get a pattern like this. Specifically, if each word was equally likely to be the answer, the probability of hitting this pattern would be 58 divided by around 13,000.
Yeah, each word equally likely. So, yeah, and what does that even mean? Like the probability of a pattern. Well, that's equal to the word being in the set of words that match the pattern. So really, when you say the probability of a pattern, you're really saying what's the probability of the words that match this pattern. You could even say that pattern in this case, like W, not E, not A, not R, not Y, and A is somewhere in here. Pattern is equal to this.
Of course, they're not equally likely to be answers. Most of these are very obscure and even questionable words. But at least for our first pass at all of this, let's assume that they're all equally likely and then refine that a bit later. The point is, the pattern with a lot of information is, by its very nature,
Yeah, this is a lot easier to think of when, in terms of subset of the sample space.
likely to occur. In fact, what it means to be informative is that it's unlikely. A much more probable pattern to see with this opening would be something like this, where of course there's not a W in it, maybe there's an E, and maybe there's no A, there's no R, there's no Y. In this case, there are 1,400 possible matches. So if all were equally likely, it works out to be a probability of about 11.
So we can say the probability of this pattern. See the probability of, yeah, this pattern right here is equal to the sum of probability of words wait, what are we doing? Sum, oh no, words such that the word matches this pattern. The word matches this pattern. And all those probabilities are equally likely. So it's just equal to, let's call this W. And so it's just equal to, the size of W times the probability of W. And so that's just equal to the size of W times 1 over 12,972, which is just equal to the size of W over 12,972.
That this is the pattern you would see. So the most likely outcomes are also the least informative. To get a more global view here, let me show you the full distribution of probabilities across all of the different patterns that you might see. So each bar that you're looking at corresponds to a possible pattern of colors that could be revealed, of which there are 3 to the 5th possibilities, and they're organized from left to right, most common to least common. So the most common possibility here is that you get all grays. That happens about 14% of the time. And what you're hoping for when you make a guess is that you end up somewhere out in this long tail, like over here where there's only 18 possibilities for what matches this pattern that evidently look like this. Or if we venture a little farther to the left, maybe we go all the way over here. Okay, here's a good puzzle for you. What are the 3?
I mean, that's nice. Yeah, if your pattern crunches down the sample space to the smallest possible size, then that's good.
In the English language that start with a W, end with a Y, and have an R somewhere in them. Turns out the answers are, let's see, wordy, wormy, and Riley. So to judge how good this word is overall, we want some kind of measure of the expected amount of information that you're going to get from this distribution. If we go through each pattern and...
Okay, yeah, this is where I have to...